Okay, students, welcome to the third and, or I guess the sixth and final video in this topic of thermal physics. And in this video, I'm going to talk to you about some very, very basic concepts of thermodynamics. Now, I should explain up front that thermodynamics is a very, very complicated and deep topic, and we're just barely going to scratch the surface. So what we're going to do is we're going to basically apply the concepts that we learned when we use the ideal gas law, and essentially we're going to apply those in a graphical sense to thermodynamics. That's what this is going to amount to. You can go far, far deeper in this topic, but this is just a very, very basic introduction to you, okay? All right. So thermodynamics, in order to understand what's happening in a thermodynamic process, we have to clearly understand what the system and the surroundings are. Okay, remember that this idea of heat is the energy that flows between two objects as a result of temperature differences. And we said that internal energy was the total amount of energy of all molecules in a substance, can be kinetic, potential, etc. We're going to call internal energy, we're going to give it this variable big U. Okay, so whenever you see that, I want you to think internal energy. Okay? All right. We also talked about the average kinetic energy of the gas molecules, where V was the RMS speed, okay, being 3/2 kT. Okay, so here's a question for thought before we launch into this, right? If I have a flask containing gas molecules at 300 Kelvin, okay, and if I take that on an airplane, and when the airplane is at its cruising altitude, does the temperature inside the flask rise? Of course it doesn't. That would be ridiculous, okay? So this really highlights in a very elementary way the difference between systems and surroundings. So the system is the complete set of objects under consideration. In this particular case, of the flask containing the gas molecules, the system would be that collection of molecules at 300 K. Okay, it's not that plus the airplane or the Earth plus the airplane plus the flask. Okay, it must be very clear what you're talking about. So in this case, the system can be either the pot and the water, it can be just the water, it can be the pot, it can be the fire, it can be whatever, but you have to be very, very clear what the system is that you're talking about. Okay. Now, the system can be open or closed. If it's open, mass can leave or enter. If it's closed, no mass can leave or enter. If it's isolated, then nothing of any form leaves or enters at all. Okay? So any processes that change the state of a system is called a thermodynamic process. The surroundings would be everything else outside of the system. Now, a couple of things to keep in mind. Work can be done on a system by its surroundings. The system can do work on its surroundings. We always have the same, we always have thermal energy loss to the surroundings of a system, no matter how careful we are with insulation. But usually what we do is we ignore this mathematically. It just makes the math a lot simpler. Okay. Now, if you check out this video, which is an amazing video, okay, it's a guy with a sledgehammer, cinder block, board with nails. There's this poor guy underneath. Okay. Think about what systems and surroundings are in this video and what's doing work on what. Well, it's very complicated, right? So on the one hand, this guy is doing work on the sledgehammer. Well, that's one system. Okay, the sledgehammer is doing work on the cinder block. The cinder block is actually doing work on the board. You can actually refine this down and talk about lots of different systems and surroundings. It doesn't matter how you do it. It depends, the way you define it depends on what physical mechanism you want to investigate, right? So if you want to investigate how the sledgehammer imparts a force to the cinder block, then your system would be just that isolated system right there. And you really don't care about the guy swinging the sledgehammer or what he had for breakfast that gave him the chemical potential energy to do work on the sledgehammer. Okay, so you see it can get somewhat complicated. Okay, remember that in our study of thermodynamics, the three variables that we considered were pressure, volume, and temperature. We did not fiddle much with the number of moles. Okay, now we could plot all of these together in three-dimensional space, since they all affect each other, and this is what they would look like. It'd be a three-dimensional function where the function would be f of p, v, and t, like this, okay? It would be curved and complicated, all right? But it would look something like this. Note how v and t are linear, p and t are linear, and p and v are curved because of the three situations that we dealt with, the specific cases of the ideal gas law, okay? So here's your PT, your PV, and your VT. Remember these three graphs. Now, we could deal with everything in 3 dimensions if we want to, but dealing with it in pieces in 2-dimensional space is much, much easier. But I just want to point out that you could visualize it in 3 dimensions. Okay, now all processes can be plotted on what we call PV diagrams, which are pressure against volume diagrams. You're going to see these a lot. This is kind of the standard in chemistry and physics dealing with thermodynamics. Remember the ideal gas equation? PV equals nRT. So for a constant T, the graphs look like this. Remember, PV is a 1 over relationship, is an inverse relationship. P against 1 over V would be linear. And we said that the upper curve was a higher temperature and the lower curve was a lower temperature. Higher temperature has a steeper slope in this case, okay? These lines are called isotherms. And this term isotherm is important. Iso, the prefix iso means that things are the same. So it's a line of the same temperature, isotherm, okay? All right. Okay, so if I consider a gas in a chamber as being the system, okay, so that's this area, that's the stippled area inside of this chamber, that's my system, okay? And if the chamber has a movable frictionless piston of area A, which is right here, and the volume expands if it's heated, so I'm giving it internal energy here, okay, it will expand, meaning that the piston moves from position 1, let me get my pen here, from position 1 right here to position 2, okay? So again, it's an isolated system in terms of no mass is able to get in or out, okay? The volume expands by heating it, okay? All right, the piston moves through this distance x. If we assume P1 inside the chamber is constant, the gas does work pushing the piston against F2, okay? F2 is the atmospheric pressure outside of the chamber, okay? Since P1 is constant and P1 is obviously greater than P2, that means that F1 is greater than F2. Make sure you follow my logic here. Now, since work is force through a distance, the work would be P1 times A, which is the force, okay, times X, okay? But AX is delta V of the gas in the chamber, delta V being the change in volume, okay? So the work done would be P delta V. And this is a very, very, very important consideration that we're going to deal with in thermodynamics and PV diagrams in terms of analyzing them. Very important, okay? Therefore, this is what's so cool about this. The area under a PV diagram, whether it's curved or straight line or whatever, is the total work done during a process. But this process, in this particular case, if it's horizontal, this is called an isobaric process. Iso meaning the same, baric, think about barometric pressure. This is a constant pressure situation, okay? So in this case, the work done in going from volume 1 to volume 2 is just the area of this shaded region. So V1 would be here, and V2 would be over here, okay? So pretty straightforward stuff. Now, if an amount of thermal energy, delta Q, is added to the system, then two things must be true, okay? Number one, the system's internal energy increases. In other words, if you give thermal energy to a system, its temperature might go up, okay? That's delta U you can think of delta U as being its temperature, okay? And or the system can then do work on something else. So this is the work energy theorem in action. You give something energy, you're enabling that thing to do work on something else, okay? In other words, delta Q equals delta U plus delta W. This very important consideration of physics is called the First Law of Thermodynamics, okay? And you need to be generally aware of this, okay? And it makes sense. It's really just a statement of the conservation of energy and also the work energy theorem. You put energy into a system, the only things that can happen is that system can do work and or that system's internal energy increases, right, if it's a closed system, okay? So due to the conservation of energy, the heat added to a gas must equal the increase in internal energy plus the work done by the gas in the surroundings. It may be that the work done by the gas in the surroundings is zero, in which case all of the heat, all of the thermal energy is manifested as an increase in internal energy and so forth, okay? If heat is taken away from the gas, then a decrease in internal energy and negative work, okay? And negative work refers to the surroundings doing work on the gas. So if the gas is doing the work, it's positive. If there's work being done on it, it's negative, okay? These are both statements of the first law of thermodynamics. Okay, so again, the first law is nothing more than a statement of the conservation of energy. This is it right here. Okay, just if you ever forget, just remember the diagram of the potato. Okay, and this is actually in your data booklet anyway. To find the work done, okay, we just rearrange this equation, delta Q minus delta W. To find the change in internal energy, again, rearrange it. A couple of things: positive delta Q, thermal energy going into; negative delta Q, thermal energy going out of. Okay, that's straightforward. If the internal energy of the system is increasing or increasing temperature, positive delta U. If it's decreasing or getting colder, negative delta U. If the system is doing work on its surroundings, positive, which results in a positive delta V, positive V. So it would be an expansion. Okay. If the surroundings are doing work on the system, then it's a compression, and that's a negative W. Okay. Okay. So let's jump right into an example. Example 1. A gas in a container where the piston expands isothermally. Okay, what's the work done by the gas? Since the energy given to the gas is positive, and T is a constant, and delta U is 0. So from the first law of thermodynamics, we have that delta Q equals delta W. So the work done by the gas is exactly what was exactly equal to the thermal energy given to the gas, which is 10 to the 5th joules. Okay, try this one. Increase of internal energy, again, first law of thermo, I'm solving for delta U, I get 315 joules. Notice how careful I need to be with my positives and negatives, and that is a negative sign. That is crucially important, okay? So you can see how important it is to keep track of what's doing work on what, and what's absorbing thermal energy, and and so forth with your positives and negatives. Okay, I'm going to talk about different types of processes here, okay? The first one, I'm going to talk about isochoric processes. And what an isochoric process is it's an isovolumetric process when the volume is kept the same, okay? So now suppose that the piston, that movable piston chamber, suppose the piston is fixed in place and heat is added or removed from the gas chamber. Now, if you add heat, what's going to happen is the temperature is going to go up, okay? So constant V means a vertical situation on a PV diagram. So you're going from higher to lower, or from lower to higher pressure. You're going to cross an isotherm. You're going to end up at T1, going to T2, where T2 is greater than T1, okay? It's called isochoric heating. And remember, these are called isotherms, okay? Going down, at a constant V, if you decrease the pressure, the temperature decreases. This is isochoric cooling, so you're going from a higher isotherm to a lower one. If you need to find T2 in a problem-solving situation, you can always then use the ideal gas law, okay, in this form where V1 equals V2, as we did before. Okay, so here's an example of this. Go ahead and pause the video and try this one on your own. You know that you have an isochoric or isovolumetric situation when you have a vertical process on a PV diagram. Okay, so how much work has the system done? 0. Why? Because delta W is P delta V, and delta V is 0 in this case. Okay, so in isochoric or isovolumetric situations, the work done is always 0. Okay, the heat flow is into, so delta Q is positive. Using the first law of thermo, I get 750 joules. Okay, and here's an application of the ideal gas law. The pressure at 2 is 300 times 10 to the 3rd pascals. Okay, isobaric, constant pressure. Now suppose that the piston is free to move, but the gas is maintained at a constant P. This refers to a horizontal movement on a PV diagram. So again, if P is the same, you're going horizontally. Clearly, you're going from a lower to a higher temperature, remembering the sort of the rule of isotherms, and that's called an isobaric expansion. Going to the left, it's an isobaric compression, okay? All right, and you're going from a higher to a lower isotherm. Again, if you need to find T1 or T2, use the ideal gas law, noting that P1 equals P2. Similar situation, right? So pretty simple stuff if you just remember isotherms and what's a higher temperature and what's a lower temperature. As an example, try this one. Okay. All right. Is the gas gaining or losing energy? Since T is increasing, the gas is obviously gaining energy. Delta W is always positive in isobaric expansion. So note immediately that I put that it's an isobaric expansion. Delta W is 16,000 joules, or 16 kilojoules in this case. Okay, another example, a piston moves so as to now compress a gas. The gas stays at a constant pressure. Isobaric, you should recognize that right away. Okay, W positive or negative, Okay, it's negative because it's a compression. Delta W, okay, P delta V, that's 90 joules. Actually, it's, I guess, negative 90 joules. Okay? Okay. And the last case is an isothermal process. In this case, the piston is free to move, but it's pushed and pulled very, very slowly. Thermal energy has time to enter or leave the system, and so the system and the surroundings are at the same T always. Now, this is a case where a process would actually follow a curved, an isotherm. This is called an isothermal expansion. So it starts off here, and it ends up here. The amount of work done, again, is shown by the shaded process here, which unless you're going to use calculus and know that function, which actually you do know the function, unless you're going to use calculus, you'd have to estimate the area of that trapezoid, okay? Going down or going up, so isothermal compression is going up an isotherm, isothermal expansion is going down an isotherm. Again, you need to find P2 or V2, use the ideal gas law, noting that T1 equals T2, okay? Okay, here's an example. All right. Calculate the temperature of the gas in state B. This is a great example, okay? So I'm setting up my ideal gas law application here. I get 400 K. The values here simply are just read off of the graph. Notice the powers of 10 on the X and Y axes, okay? The work done going from state A to state B, okay, is the area under the graph. It's very, very straightforward, okay? 2,400 joules, all right? Okay, continuing this example, determine the amount of thermal energy transferred from state A to B. Okay, the ideal gas law, because it's isothermal, delta Q equals delta W. Okay, turns out actually that TB minus TA is 0. It says note that the process AB is actually not isothermal. Okay, now the gas is and how do you know it's not isothermal? Well, it's because it's a straight line, it's not a curve, okay? For example, if the gas goes isothermally from B back to A, it's going to be a curve going up like that because isotherms are always curved, okay? All right? So we want you to draw that, okay? State and explain whether the magnitude of the thermal energy transferred in this case would be less than, equal to, or greater than the thermal energy transferred in C. Okay? It would be less than because the area under the curve is less than the area under the straight line. Okay? Very cool. All right? And example 7. This is a little more complicated. This is the most complicated stuff you'll be doing with thermodynamics. Okay? Turns out that 1 gram of water becomes a lot of steam when boiled at a constant pressure. Calculate the work done by the water when it vaporizes. This question is going to take you a while. So pause, get some paper and a pen and a calculator and try to work this one out. Okay, the work done by the water when it vaporizes. Okay, I'm using delta W equals P delta V. I'm actually visualizing it as a PV diagram here. Okay, I get that P delta V is positive 169 joules because I'm going from V1 to V2. Okay, it's an expansion because it's going from 1 cubic centimeter to 1671 cubic centimeters. Okay, continued. Calculate its increase in internal energy. I know that the heat I can figure out using latent heat of vaporization here. The heat added to the water is 2256, combined with the ideal gas law. Okay, delta U is 2087 joules. Pretty cool stuff. To vaporize 1 gram of water, what this means is that we have to add that many joules of heat. Okay, that's a lot of heat. Most of this added energy remains in the system as an increase in internal energy. The remaining 169 joules leaves the system as work done in the surroundings and expanding from a liquid to a gas. And of course, that's how steam engines work, right? Okay, but it's really actually not that much energy as a percentage of the added energy originally. Okay, last thing I'm going to talk about is PV diagrams and what I call thermodynamic cycle, okay? Often we look at cycles on PV diagrams. A cycle is just a PV diagram where you end up in one place, or you end up in the same place where you started, okay? So for example, you go from A, B, C to D and then back to A in this particular diagram. This is called a cycle, okay? We can figure out the amount of work done in each part of the cycle. Obviously, in this case, from B to C and from D to A, there's no work done because delta V is 0. Okay, so for the whole cycle, the net work done by the gas is the enclosed or shaded area right here. Okay, because remember this is positive work and this is negative work. So when you add it up all together, you're actually figuring out the area of that box, that shaded box, okay? For any cycle, that's how you find the net work done by the gas. Now, this work could actually be used for something. Okay, this is what's called a heat engine, all right? In thermodynamics, when you're using work to do something useful, it's called a heat engine in a cycle.